I welcome you all to the session of applied thermodynamics, and today we shall discuss about the regenerative method. You know that we have discussed about the improvement of Rankine cycle efficiency, and in the context of this aspect, you know, we have discussed about superheating and also reheating. Now, we have, if we try to recall, if we try to draw the schematic depiction of the steam power plant. So, this is boiler, so this is turbine, four. Now, if we try to draw the TS diagram, we see that so this is the TS diagram. Now, you can see that even if we go for superheating, right, the ideal Rankine cycle that we have discussed, wherein steam will start expanding, I mean the state point 3 prime is the state of steam before it enters into the turbine. This is for the ideal Rankine cycle. Now, as we have discussed that we can go for the superheating method, by which we can increase the temperature of steam beyond 0.3 prime and we can superheat up to 0.3. Now, in both the cases you can see either it is steam will start expanding in turbine from 3 prime to 4 prime if it is not superheated, I mean if we do not go for superheating the steam, but if we go for superheating the steam beyond 0.3 prime, then steam definitely will expand from 3 to 4, that is in the turbine, and that is what I have shown the schematic depiction here. See here we are trying to increase efficiency. Again if I try to write, our objective should be to increase efficiency. This is the efficiency of the ideal Carnot cycle, and we have studied this cycle only because to analyze all the real cycle, all real cycles performance with the ideal Carnot cycle. So, now according to the Carnot efficiency, if we can reduce this fellow, if we can reduce this TL, if TL decreases or TH mean I will be talking about increases. So, there are two ways, either two ways by which we can increase the efficiency of the cycle, either by decreasing TL, but as I told you in the previous classes that we really cannot decrease TL, otherwise I mean we can decrease TL, but in doing so we are going to invite another problem. Now, what we can do, we can increase the mean temperature of heat addition, right, and that is what I was discussing in the last few classes. So, if we now look at that without if we try to increase temperature of steam beyond 3 prime, we all are doing essentially to increase the average or mean temperature of heat addition. Now, fine, we can increase, definitely we can superheat steam, that is not bad, because it not only improves the efficiency, but also increase the quality of the steam. So, it is also quite I can say advantageous from the perspective of the lifetime of the turbine blade. So, can't we look at one important point, because our objective today is to regenerative method. So, I am writing regenerative analysis. Why do we need to go for regeneration? What do we mean by regeneration? Now, if we look at this particular part, that is heating from T2 to T2 prime. See, we are having in this Rankine cycle, we are having this component of heating, that is this sensible heat transfer, right. So, and this heating takes place at a relatively lower temperature. So, this is that is T2 and this is T2 prime, T2 and T2 prime. So, T2 is less than T2 prime, that is quite obvious, because we are pumping liquid, that is also normal temperature. Now, we are heating. So, basically we are increasing temperature of the feed water. So, the water which is being fed by the pump to the boiler, right, that temperature first increases from T2 to T2 prime, and that heating takes place at a relatively lower temperature, right. And you try to understand, we have discussed in the last, I think one of my previous classes, that this component, this part of heating lowers the average or mean temperature of heat addition. So, definitely we can look into all these aspects like superheating steam and then reheating, but why can't we look at this particular aspect? Can't we think about increasing the temperature of the feed water before it enters into the boiler? If we do so, then perhaps we can increase the mean temperature of heat addition, and which in turn, if we increase the mean temperature of heat addition, so this is TH mean for this particular case. So, I did not write TH mean for the ideal Carnot cycle, but it is TH max for ideal Carnot cycle, that is TH max. So, it is eta thermal Carnot equal to 1 minus TL by TH, this is max. Now, our objective should be to bring this mean temperature of heat addition in the ideal Rankine cycle. If TH mean becomes closer to TH max, we can reach the ideal Carnot cycle efficiency. Okay. So, you try to understand, our objective should be to bring TH mean closer to TH max. In that case, we can really reach the efficiency of ideal Rankine cycle, very close to the ideal Carnot cycle efficiency. Now, as I discussed, we can go for superheating and reheating, those aspects we have already discussed, but we can't really ignore this part, that instead of T2 to T2 prime, that heating is done. So, before we supply water to the boiler, can't we increase the temperature of feed water, so that this component, the sensible heating component can be reduced, and if we can reduce this sensible heating, low temperature sensible heating, then it will increase this TH mean closer to TH max, and we can increase the efficiency of the cycle. So, the idea is to reduce the heating, the low temperature heating of the feed water, right. So, this is very important. So, our objective should be to increase the mean temperature of heat addition by reducing or eliminating. If we can eliminate it, that is well and good. If we cannot eliminate it, we can reduce. So, if we can reduce this amount of sensible heating, low temperature sensible heating, we can raise the average temperature of heat addition, and it will eventually be closer to the TH max, so that we can achieve almost the Carnot cycle efficiency. So, reduction of the low temp, I mean to eliminate, either to eliminate or reduction in this low temperature heat addition, which is nothing but sensible heating I am writing. Sensible heating, we can increase the mean temperature of heat addition, and this could be made possible by making use of the regenerative analysis. Okay. So, I am writing here that very important that mean temperature of heat addition can be increased by reducing or eliminating. I am writing this word eliminating the low temperature of heat addition low temperature of heat addition of feed water in boiler, and this could be made possible by making use of the regenerative analysis, regenerative principle. So, this is what is regenerative. Now, having understood this, what do we mean by regenerative? So, basically regeneration is nothing but to increase the mean temperature of heat addition by either by eliminating or by reducing the low temperature of heat addition of feed water in boiler. So, see now if I go back to the previous slide, you can see that when feed water is pumped to boiler. So, before it goes to boiler, if we can increase the temperature of feed water by some other means, then perhaps we can increase. So, if we increase the feed water before it enters to the boiler, then perhaps we can increase the mean temperature of heat addition. So, this can be done either by by using several means that we will discuss, but question is, I mean now you think it because we all are engineers. So, we have to think it from engineering point of view. What will happen, that without going into much but mathematical analysis and thermodynamic analysis, you try to understand whatever you have understood from your heat transfer course. See, when feed water is pumped to the boiler and essentially you are supplying heat to the boiler. Now, upon receiving heat from the combustion of coal, if it is coal fired boiler, the water temperature first will increase from T2 to T2 prime. Now, if we somehow can provide temperature, the feed water temperature will be T2 prime, then perhaps this amount of temperature increase will not be there in the boiler and we can save the fuel cost, right. So, if we can increase the temperature of feed water from T2 to T2 prime before it enters the boiler or into the boiler, then we can save the fuel cost associated with that particular heating, and in that case we can increase the efficiency, because you understand here we will be having W out. So, the net work output, this is W in and this is Q out. So, the net work divided by net heat input, that is nothing but the Q in is equal to the efficiency. So, if we can reduce the Q in, then efficiency can be increased. So, efficiency also can be viewed as W net divided by Q in. If we can reduce Q in, we can increase efficiency and it will be closer to the ideal Carnot cycle efficiency, right. By how? So, the amount of fuel that will be required to increase the temperature of feed water from T2 to T2 prime, if we can save it by having some other means, then perhaps efficiency of the Rankine cycle can be increased. And those ways, those avenues are very important and are known as the regenerative methods. So, now what we will be doing now? So, you can see one way. So, one way to increase the temperature of feed water is as follows. So, feed water is allowed to pass through tube placed inside the turbine. So, let me draw the schematic depiction that will help you to understand what I would like to discuss now. So, what I am telling, it would be nice, say this is boiler and then this is turbine. So, we will be getting W out and the steam will expands and it will be collected, it will be allowed to pass through condenser wherein we will be having heat rejection and then it will be collected and that collected condensate will be pumped okay. So, this is, let us say this is 1, this is 2, this is 2 prime, this is 3 and this is 4, right. So, this is a special arrangement. You can see that, I mean if we now compare this schematic with the previous one, in this case directly feed water, the condensate collected from the condenser is pumped back to boiler without taking that particular water into the turbine. But here what we can see? We can see the condensate that is collected will be pumped through a circuit which is placed inside the turbine, right. So, when water is allowed to pass through the circuit which is placed inside the turbine and steam is expanding, right. So, this is basically a counter flow type heat exchanger. Turbine will now is acting as a dual performer. So, basically turbine is allowing steam to expand and while steam is expanding it does work on the rotating part of the wheel, we are getting work output. On the other hand, since the circuit is placed inside the turbine and water will flow in the opposite directions to the steam flow. So, this is the steam flow direction. So, this is steam flow direction and this is water flow direction, right. So, steam, as if the turbine is now acting as a work producing device, it is also now acting as a counter flow heat exchanger. So, when water is passing through the turbine through the circuit and which is the movement or rather the direction of water flow is in the opposite direction to the steam flow and the water will be heated by taking heat from the expanding steam. So, there will be heat transfer, heat will be transferred from the expanding steam because steam is having high enthalpy, right, temperature is high. So, that temperature will be transferred from steam, expanding steam to the water. Eventually, when water will be entering into the boiler, that is the thermodynamic state at 2 prime. So, water temperature at state point 2 will be definitely higher than the water temperature which it had at point 2. I mean the temperature of water it had at state point 2. So, now you can see that perhaps by taking heat from the expanding steam we can save the fuel which would have been required to increase the temperature from T2 to T2 prime if we had passed water directly to the boiler. Okay. So, in that way we can save the we can increase the efficiency of the plant, and this is called ideal regenerative cycle. So, I am writing, so this is ideal regenerative cycle. Okay. So, this is ideal regenerative cycle. Now, question is you may ask me a question that using this ideal regeneration method we are still having a few, rather I can say one important disadvantageous feature, which is that see when steam is expanding in this direction definitely it will exchange heat with the water that is flowing in the reverse direction. While exchanging heat, steam temperature may fall at the exit of the turbine. So, perhaps the problem associated with the high moisture content and of steam which will eventually lead to turbine blade erosion will be there. So, the possibility of having high moisture content of the steam which will leave from the turbine will be there, and it may lead to turbine blade erosion. So, I mean the concept is somehow we have understood. The concept is that to take heat from one part of the cycle and that heat will be added to the working substance in another part of the cycle, right. Try to understand, let me tell you again. So, the ideal regenerative cycle, though it is not feasible, because maybe we can increase temperature of water from T2 to T2 prime. To increase that temperature we may reduce the steam temperature, and the quality of the steam leaving the turbine may have maybe vulnerable to the turbine blade erosion. So, instead of allowing water to pass through the turbine inside the turbine, what we can say, because ultimately steam will be in contact with the tube which is passing through the which is placed inside the turbine. So, the concept is we can take certain amount of heat from one part of the cycle, and that heat will be utilized to increase temperature of feed water in another part of the cycle, and that is nothing but the regeneration. Okay. So, we are regenerating, so we do not require additional amount of fuel to heat up that water, feed water. Rather, we are taking certain amount of heat from one part of the cycle, and that heat will be utilized to increase the temperature of feed water in another part of the cycle, and that is nothing but regeneration. Okay. So, since this is having one serious problem, that the turbine blade will be the lifetime of turbine blade is very important. So, knowing fully that the steam quality of the steam may deteriorate at the exit of turbine. So, we cannot go for this particular method, but still there are so many other methods. That what are the methods? Instead of allowing water to pass through the coil which is placed inside the turbine, what we can do, we can have separate chamber. We can have a separate chamber in which water will be allowed to mix with certain portion of steam that will be extracted or bleeded, right. So, we can have steam bleeding or steam extraction, and that steam from maybe after doing certain work, after doing work we can extract certain, or you can take certain amount of steam from the turbine, and we can allow that steam to be mixed with the water or condensate which is coming from the condenser. In that way we also can increase steam. Now, if we do like this, perhaps the expected problem of having turbine blade erosion can be avoided. So, let us quickly do, if we for these particular things, if we do the analysis, see if we go to the next slide, let us draw the TS diagram. So, this is if we try to process, if we try to map all the processes for this particular cycle in TS plane, then probably it will help us to explain in a better way what do we mean by regeneration. Okay. So, we can write like this. So, let me okay. Now, say this is T, so this is T max. So, this is T H, okay, and this is T L. So, this is condenser pressure. You know this, the several processes that you have studied from thermodynamics. So, this is condenser pressure, constant pressure heat rejection, okay, and this is also, this is the boiler pressure. Okay. So, now try to understand, if I try to draw using different color, say this is the process 2 prime, right, and 3. So, if we go to the previous slide, so 2 to 2 prime, that heating will be done, but that heating will not be there in the boiler, rather that will be there inside the turbine by making use of this special arrangement. Now, you know that when steam expands inside the turbine, steam temperature will fall because of this particular heating. So, now 3 to somewhere 3 prime. So, the heating, so you know that T2 minus T2 prime. So, T2 prime minus T2, that will be equal to T3 minus T3 prime. Say if we assume that the processes of heating is reversible inside the turbine. Okay. So, if we try to draw the schematic, say it is, so this is, so this is, and then it will expand up to 4. So, this is 4, this is 4 prime. So, this is 3 prime, say this is 3 prime, okay, and that is 1 prime, and this is 1. Okay. So, now let me explain you. So, you can see the temperature of water increases from T2 to T2 prime, and this is 3, and temperature of steam will drop from T3 to T3 prime, right. Question is, we consider that this heat transfer takes place following reversible process. If it is reversible process, so that is quasi static process. So, I mean the process is reversible, internally reversible process. Okay. So, now if that is the case, we can write, so we write that we assume that heat transfer. So, this is I am writing heating of feed water takes place reversibly. Then T2 will be equal to T3 prime and T2 prime will be equal to T3. So, this is very important to understand. If we assume that the heat transfer takes place reversibly, then these two temperatures will be equal, and in that case the path followed by steam and water will be equal to exactly equal. Okay. So, that is I mean if the process is reversible, then at any section, I mean if we draw a line, at any point steam temperature must be equal to the water temperature, right, quasi statically, almost they are in equilibrium condition, right. So, that is the concept you have studied in thermodynamics. So, at any point between the heating and cooling process, temperature of steam and water will be equal, and that as a result of which you know that the path followed by steam will be exactly equal to the path followed by the water, right. Now, we can write, so ds water, right, ds water equal to del cube by T water will be equal to minus del cube by T steam equal to minus ds steam. Quite obvious, you have studied second law. So, you can increase, heat will be gained by water which is allowed to pass through the coil. So, entropy of water will increase, but there will be transfer of heat from the flowing steam. So, entropy of the steam will decrease. So, that is why it is written minus ds of steam, but we have written this formula because we had considered this is reversible process. So, there is no entropy generation, and that is why I told you, again I am telling, the path followed by steam while expanding or while releasing heat or while transferring heat to the water will be exactly equal to the path followed by water, that is 2 prime and this 2 process. Okay. We can write delta S water. So, you can see this is delta S water and this is delta S steam. So, basically we can write delta S water equal to delta S steam, right. Say I am giving name, this is A prime, B prime. So, this is possible if we consider the process, this heating and cooling processes are reversible process, right. There is no entropy generation, we can use this expression. So, this is highly for the reversible process, and you can see the minus sign has come only because of the reduction in entropy. So, but the gain in entropy by water is equal to the loss of entropy by the steam. Okay. So, this is the equation. Now, I mean you can see after expanding, say the steam temperature will drop from T3 to T3 prime, the remaining expansion takes place isentropically, right. So, after this the remaining expansion will takes place isentropically, that is 3 prime to 4 prime, right, fine. Now, question is what is regenerative heat? So, you can understand regenerative heat, that is Q into delta S. So, Q regen. So, see this is the 2 prime. So, if I take different color, so this is the regenerative heat, right, and if I take another color for this part. So, since the processes are reversible, so this area under this process line will give you the regenerative heat. So, that heating is equal to the cooling, right. So, that you can see from this TS diagram. So, that is nothing but area under the curve, I can write so equal to area. So, I am let me write using green color, area, what is 2 prime A 2 equal to area, I mean, so let me, I have to hatch this part again. So, this is the area and also, so this is the area. Okay. So, now area is 3 prime, or I am writing 3 prime 3 4 B prime B. So, this is the area B prime, let me write 3 prime. So, this is the area. So, that is the, I am writing this is Q dot gen. Okay. So, this is Q regen, this is also Q regen. Okay. Now, See, I can from this particular schematic, just I can tell you from this TS diagram we can write that. So, this is 1 prime. So, this is 1 prime, this point is 1 prime, this point is 1, this is 4 prime, this is 4. Okay. So, from this TS diagram can we write that S1 prime minus S1, that is delta S water equal to delta S steam, if we try to write. So, delta S water equal to delta S steam. So, this is S1 prime minus S1 equal to S4 minus S4 prime. So, from there we can write S4 minus S1 prime equal to S4 prime minus S1, right, equal to delta S. Very simple to understand. So, delta S water equal to delta S steam, delta S water is nothing but S1 prime minus S1 and this is S4 minus S4 prime, that is delta S steam. So, by doing this algebraic manipulation we can write this is the expression delta S, right. So, now it is very important that from this ideal regenerative cycle, let me draw the cycle, I mean TS diagram again. This is TS. Okay. So, if we try to draw, right now, if we try to draw. So, this is ideal regenerative cycle, it is not superheated, steam is just saturated vapor, and then if we redraw the processes, say this is 2, this is 2 prime, this is 1 and this is the process, right. Now, so this is 3 prime, this is 3, right, and then this is 4 prime, this is 4 and this is 1 prime, right. So, we try to understand that we see that in the ideal regenerative cycle, right, this 1, 2, 2 prime, 3, 3 prime, 4 prime. So, 1, 2, 2 prime, 3, 3 prime, 4 is exactly equal to the Carnot cycle, which is that 1 prime, 2 prime, 3, 4. So, 1 prime, 2 prime, 3, 4, let me, I mean if I use different color. So, 1 prime, 2 prime, 3 prime, 1 prime, 2 prime, 3, 4. So, this is the Carnot cycle. Okay. So, this is now area 1, 2, 2 prime, 1, 2, 2 prime, 3, 3 prime and 4 prime. So, this area is equal to the Carnot. See, try to understand this, these two are equal from the TS diagram you can understand. So, if I try to draw using say red color. So, I am talking about, so this is the area, right. So, try to understand, since this delta S equal to delta S steam, delta S water equal to delta S steam, from this TS plane you can see the area 1 prime, 2 prime, 3 and 4 will be equal to the area 1, 2, 2 prime, 3, 3 prime, 4 prime. What does it mean? It indicates that the area of the ideal regenerative cycle. So, ideal regenerative cycle, efficiency of the ideal regenerative cycle is equal to the ideal Carnot cycle. So, try to understand why we are doing this exercise, essentially to establish that by doing this regenerative principle we can increase efficiency of the cycle closer to the ideal Carnot cycle. So, right. So, by having only look at this Ts plane we can see. So, since this quantity, so basically here we can tell me, I mean you know that this equal to delta S, and if I use different color say this, so this is also delta S, right. So, I mean this is A prime, B prime, right. So, from this simple mathematical analysis, only one important assumption is that the heating of water and cooling of steam inside the turbine will take place following reversible process. If we can do so, that I mean if we make that process is infinite slow, then we can show that the efficiency of the ideal regenerative cycle will be equal to the efficiency of the Carnot cycle, and that is quite obvious, because essentially the area under the process line will give you the net work input, because for all the cases, for both the cases heat rejection is remaining same, right. So, let us do this one analysis in which so basically why this is so. So, efficiency of the ideal regenerative cycle is, I mean will become closer to the ideal Carnot cycle. This is only possible because of the increase of the mean temperature of heat addition, right. And if we can discuss that for the ideal regenerative cycle, right, what we can write, QH equal to TH, let me write here in capital. So, let me, so QH equal to TH into, so go back to what is, so this is S3 minus S2 prime, right. So, delta S, so S3 minus S2 prime, that is delta S, that is shown by this here. So, this is delta S. So, now this is, we know that delta cube equal to T into delta S, right. So, I mean if we integrate this process, then ultimately cube will be equal to TH mean into S3 minus S2 prime, and that is 2 prime to 3, 2 prime to 3. Okay. So, we can write this, that TH into S3 minus S2 prime, right. So, I am writing this is mean. Okay. So, this is nothing but TH mean into delta S, right. This delta S is nothing but this delta S. So, this is, now this is heat addition. So, this is heat addition, similarly heat rejection QL, that is nothing but TL into what, into S4 prime minus S1. So, this is delta S shown by this yellow color, right. So, let me write S4 minus S1, S4 prime minus S1, that is nothing but TL into delta S. See, these two delta S are equal. So, this delta S is equal to this delta S, that is what we have show here. So, this is delta S. Now, S4 prime minus S1, that is delta S, and that is equal to S4 minus S1 so S4 minus S1 prime equal to S4 minus S1 prime is equal to S4 prime minus S1, that is we have already proved. So, now if we show the efficiency, therefore, so efficiency will be equal to, thermal efficiency will be equal to, so this is regenerative equal to is equal to one minus TL into delta S by TH into delta S. So, this is not Carnot. So, I can't write 1 minus TL by TH, rather we can write 1 minus QL by QH, right. So, it follows that 1 minus Q L by Q H. So, that is nothing but 1 minus T L by T H. So, we have been able to establish that only by having this regeneration we could increase the efficiency of the ideal regenerative cycle and we could increase up to the Carnot efficiency, right. So, this is what I wanted to discuss today, that, and in fact, if we try to summarize, by doing this simple mathematical analysis we have been able to establish that by increasing temperature of feed water before it enters into the boiler, we can increase the efficiency of the cycle up to the extent which it, I mean up to the extent of the Carnot efficiency. So, though the ideal regenerative cycle may not be feasible in practice because of its disadvantageous feature, that the moisture content of water, moisture content of steam leaving the turbine will increase and it may lead to turbine blade erosion, but there are several other means by which we still can have regenerative regeneration, and those aspects we will be discussing in the next class. Thank you.